Okay, well, welcome everyone to this meeting of the virtual CICS user group. I'm Trevor Eddles. I'm CEO of iTech Limited. We're a mainframe consultancy, analysis and technical authoring organisation, and we're responsible for the content on the virtual CICS website, and we produce the newsletter, etc. And just so you know, the website can be found at virtualcics.hostbridge.com. Okay, let's start by running through the agenda for today. As usual, most of the meeting will be taken up with a presentation, and today our guest presenter is Ezriel Gross, Principal Solutions Advisor for Rocket Software, and he'll be discussing debugging CICS storage violations using IPCS. A copy of the slides from the presentation will be on the website later today. And if you missed our previous meetings, you can download copies of those presentations from our website. And you can listen again to the whole presentation. There's a link on the resources page of our user group website. So that's virtualcics.hostbridge.com/resources.htm. Following Ezriel's presentation and any questions you have for him, we'll move on to the latest CICS news and the latest CICS related articles. Feedback request is there to remind me to ask you for your feedback about this virtual meeting. And then I'll give you the dates and times for the next virtual meetings. So that's the plan. I'm anticipating that it will last for just over an hour. Anyway, as I just said, today's presentation is from Ezriel Gross. He's Principal Solutions Advisor for Rocket Software, specializing in IBM CICS tools. He was formerly CEO of Circle Software, acquired by Rocket in 2019, where he specialized in hands-on classes and consulting for CICS DB2 and MQ series. Ezriel was a gold consultant for many years and is currently an IBM champion. His specialties include web services, web support, performance tuning, internals, CICSplex, SM, DevOps, and Liberty as they relate to CICS. He recently co-architected the CPROF product, a tool that captures CICS trace without running in a CICS region. So Ezriel, I'd like to thank you very much for being with us today. And what I'd like to do now is pass control of the meeting over to you. But before I do that, can I just say to everyone, if you have any questions for Ezriel, then can you please put them in the chat and I'll pick them up and ask Ezriel as we go along.
Thanks, Trevor.
I'll stop sharing and you should be able to share yours.
My screen just went wonky. 1 second, let's try that again. Of course. There we go. Are you seeing my screen there, Trevor?
Yes, that's perfect.
Okay. Now we just have to put it into full screen mode. There we go. Okay. Well, good morning or good afternoon, depending on where you are. And I'm Ezriel Gross, again with Rocket Software. And today I'm going to be talking about debugging CICS storage violations using IPCS. So I always think that when you go through any sort of learning experience, including debugging storage violations, you really have to understand storage management itself, right? So you have to get an idea of how CICS manages storage, because it just makes it easier than if you're going to take a look at storage violations. So I'm going to go through an overview of storage management. I'm going to show you how CICS manages the individual pieces, and then I'll talk about what is a storage violation itself, right? Because you might think, well, a storage violation is anyone who violates storage, but CICS has a specific meaning for what a storage violation append or dump will look like. And that doesn't mean you can't violate storage in another way. It's just that CICS won't detect it as a storage violation, right? So storage violation to us means somebody stepping on storage, but to CICS, it has a very specific meaning. I'll talk about some of the causes of storage violations. And again, you can't get them all, but we'll talk about the ones that are most likely to be causing your problems. Then, of course, it wouldn't be a true presentation unless I talked about how to protect certain areas of storage. Again, most of the areas that you're protecting, if somebody were to step on, wouldn't show up as a storage violation. But nonetheless, you really need to understand the areas that you can protect within CICS and then what the implications are as well. Then finally, to understand storage violations, I have to go through a little bit of the storage manager internals, right? To see how CICS manages the individual control blocks, because those blocks are going to point you to the violated areas. And when you're dealing with a storage violation, you're going to find out that there's very little to help you in terms of determining who the culprit is, right? But one of the areas is if you can look at that piece of storage and you can recognize the data, that's usually the easiest way to solve a storage violation. There are other things you can do as well, as we're going to show you, the fact that you know when that storage was allocated and when you got the violation and if anybody else ran in between and so on. And then finally, we'll finish it up with true storage violation analysis, where I'm going to show you all the different ways that I analyze storage violations. Oop. We're getting some feedback on the screen there. So if you can mute your mic. So, okay, so let's start out with storage management in general, right? So CICS is just another address space. And if you worked with CICS for a number of years, you'd find out that just like any other address space, you could set the amount of storage available to your CICS region with a region parameter, right? So you can set the region size, right? And that will determine the amount of storage that CICS has available. The difference is the region size really depicts the amount of storage that's below the bar, right? So the 2 gig address space, you would get from whatever it is to 2 gig, and that would identify the amount of storage you can use. CICS added an additional parameter called Mem Limit, which would allow you to limit the amount of storage above the bar, right? Above the bar, again, we're not making much in terms of utilization of it yet, although there are a bunch of things up there. The trace table lives up there, channels and containers lives up there, temp storage can live up there, Java lives up there. So over time, I anticipate more and more things will go above the bar. And of course, we have quite a bit more storage, as you can see, 8 billion times the size of a 2 gig address space. Now, we're going to see that sometimes setting the region parameter will let you set the mem limit parameter, and you have to have a certain amount of mem limit to bring your region up. So for example, at CICS version 5.6, you can't bring a region up unless mem limit gives you at least 10 gig, right? So you're going to see that you need to set the storage parameters to enough to support at least bringing up your CICS regions. Now, within CICS itself, he breaks up that storage, right? So you have region size, you have mem limit, right, which are maximums. He breaks them up into dynamic storage areas, or DSAs, right? So above the bar, there are 3 DSAs. There's the user DSA, the CICS DSA, and the shared DSA. And in most environments, unless you're doing something in the world of Java or you're doing your own your own assembler get mains above the bar, there isn't much you're going to see above the bar, but you will see at least 1 gig in use by CICS at all times. And you're going to see that's for things like channels and containers, and again, for temp storage above the bar. Again, you can't run without a mem limit of at least 10 gig in CICS version 5.6. And then you'll see that below the bar and above the line, we refer to the maximum amount of storage for the CICS region as EDSA lim, or below the line as DSA lim. Now, you can always see what you have it set to within any CICS region. Just go into CEMT and do an inquire DSA. You could see you get some generic information, right? You'll notice we're not SOS or short on storage above the bar. So that's the other problem people tend to run into when they're running CICS, is either a short on storage situation or a storage violation. And CICS will show you right away if you go into CEMT. Of course, you have to be able to get into CEMT before you go short on storage in most cases. But if you're there, you could see whether you're SOS above the bar, above the line, or below the line. And then you'll see the DSA limb settings, right? So you can see in this environment, I have my DSA limb set to 5 meg, and then you could see how each of the 4 DSAs below the line are using storage, because CICS doesn't automatically allocate all the storage to the individual DSAs. It's on demand. So as storage is needed, it's allocated to the different DSAs. Now you can see above the line, right, but below the bar, I have about 1 gigabyte allocated. And you can see I'm not using very much in this particular CICS region, but nonetheless, that's how much I have allocated. Then finally, over here on the right-hand side, you'll see Mem Limit, and you'll see I have no limit coded. If you specify region 0 and you don't code a Mem Limit, then he'll automatically set it to no limit. Now, I don't know that there's a problem with that because, again, we're not using that much above the bar today, but it's really up to you. You can see that out of the no limit, I'm getting 1 gig in my Grande CICS DSA. That's it, right? Because I'm not making any use of shared storage. I didn't do any shared get mains. I didn't do any user get mains above the bar. So now you got these big areas, DSAs, right? You have a DSA, which is set by Mem Limit above the bar. You have EDSA lim and you have DSA lim, right? But these are big chunks of storage. Internally, what CICS does then is, as there's demand for storage, he will allocate extents, right? An extent is a fixed size of storage. It's physically contiguous. And what you'll notice is the DSA extent size is a little bit different below the line and above the line, right? Below the line, the size is generally 256K per extent, right? But if you have tran ISO set to yes, then the user DSA, even below the line, has a minimum of 1 meg, okay? Now, above the line, we tend to have the DSAs set to 1 meg extents, right? So as you get a particular piece of storage within CICS, he will allocate 1 meg extents above the line and 256K below the line, except for the user DSA in the case where you're using transaction isolation. But we'll talk about some of the protection issues, right? Now, we haven't gotten down to what a task we'll get to yet, but nonetheless, you can see now you have the global area of the DSAs, you have these extents, which are broken up into individual pieces. So finally, we'll talk a little bit about control blocks to start out here. And off the storage manager anchor, we have these things called PPAs, right? Page pool areas. Now, I don't know why they decided to call it a PPA in the internal control block and a DSA when we talk about it externally, but a PPA and a DSA are exactly the same thing, right? Page pool area is just the control block name for a DSA. And what you'd see is chained off of the PPA are these things called PPXs, page pool extents, because the contiguous piece of storage, as we mentioned just before, is either 1 meg or 256K at a minimum. Remember, if you take a program and the program is 6 meg to start out, yes, CICS will get you a 6 meg contiguous piece of storage, but the minimum size is what I was talking about before. And again, as the extents are allocated to the different DSAs, you'll have multiple extents, right? And so a DSA can have many extents, but a DSA can also have 0 extents, right? If it's not using any storage. So this is what I tend to call the storage manager food chain. This is like all the control blocks that are related to storage management, and they're all the interesting ones. I don't want to say that there aren't any others, right? I'm not talking about, you know, DXHs and DXEs and DXGs in this picture. So there are more control blocks, but these are the ones that are more interesting. So we mentioned PPA, right, which is a DSA, right? Underneath the PPA, you could have multiple PPXs, right? So you could have multiple page pool extents, and they're managed with something called the page allocation map, which would identify whether or not storage which is within the extent is used or free. So again, the DSAs use the PPXs to know what extents they have allocated to them, and they allocate storage to individual users based on how much storage is available and how much you request. And I'm just keeping it simple for now. Now, you could get a suspend queue element. If you get suspended for storage because the storage is not available to you, you end up with a deferred work element known as a suspend queue element, right? And you're suspended for a particular piece of storage. You would see SQEs in a short on storage situation, right? Not necessarily a storage violation. Now, off the storage manager anchor, you can also get to domains themselves. And what you're looking at here is a domain subpool control area. Subpool control area will manage storage within an individual subpool. So CICS breaks up the type of storage that he's going to allocate into these things called subpools. And they have different boundary values, they have different initial settings and so on. But a domain will use these SCEs, storage control elements, and SCF, storage control free descriptors, to identify out of a piece of storage what is allocated and what is free. Now, he only uses the SCEs and SCFs if the storage is variable, right? So the first thing to understand is variable storage means 1 minute I could ask for 10 bytes, next minute I could ask for 100 bytes. But there are a certain number of domain control blocks, right, that are fixed in size. And for the fixed size control blocks, IBM uses QPHs, quick cell page headers, and quick cell pages. And effectively, they take a page in storage and break it up into a header and the number of elements that can be supported based on the size of that page. However, the quick cell page headers, the quick cell pages themselves, are a much more efficient way to allocate storage, right? It's basically 2 pointer moves. So he uses it for fixed length control blocks, but he doesn't use it for variable. He uses SCEs and SCFs. Now, this is all really interesting, but at the end of the day, what we really care about is the right-hand side of this picture. The right-hand side of this picture deals with the individual tasks, right? The people that are running in the system. What we're showing you here is off the storage manager anchor, every person in the system will have a control block known as a SMX, storage manager transaction, right? And the storage manager transaction will point to the task subpool control areas. And we're going to find out in just a moment that tasks get storage below the line, above the line, and above the bar in 2 different DSAs. So at the very least, you're going to see every task get storage in 6 subpool areas. Now, even though you have the control block, you may not have any storage allocated, as we're going to see as well. And just like the domains do, SCEs and SCFs are for allocated and free storage. And so SCEs are storage control elements identifying allocated storage, and the free descriptor tells you what's left out of what was assigned to you, as we're going to see. And then one last thing, you could always get to the SMX off of the storage manager anchor, but since storage is being managed at the time your task is allocated, or I should say attached, the transaction manager transaction control block will also have a pointer to the SMX, right? So whether you get to it from here, or you get to it from here, or as we're going to show you, get to it from IPCS, we're going to be mostly interested in this picture, task SCAs, SCEs, and SCFs. So again, we mentioned what domain subpools are, but they're allocated early in life, and I'm going to show you an example of them. And effectively, they separate out the storage that domains use for different types of things, certain types of control blocks, where do your transient data or temporary storage control blocks live, and so on. And then there's task lifetime storage, which is more interesting to us because we're in the midst of debugging storage violations. And when we're going to actually take a look at storage violations, we're going to be mostly interested in the life of task storage, right? So let's have a look at a dump. I'm just going to jump over to TSO and hope my session is still, yep, I'm still connected. So I'm in IPCS. Let me just show you. I have a storage violation dump here. You can see the code is in SMO 102. SMO 102 or SMO 103 is a well-known message code for storage violations, and this dump is open right now. I'm going to go to option 6 for free form. I'm going to issue a verb exit for DFHPD 730, and I'm going to take a look at SM equal 1, right, which is basically the summary of the storage manager. Now, if you're not familiar enough with IPCS, I'm sure you can go onto Trevor's website. I did an intro to IPCS for sysprogs. You can take a look at that. It'll show you what it is we're looking at. So when I hit enter, I'm going to show you that it's going to give us the summary of storage management, right? You can see SM equal 1. And then what I'll also show you is every dump starts out with a dump summary, right? And the dump summary will just tell us the same thing, storage violation, but we'll go through some of the other parameters over here as well, because he's actually telling you the Apple ID of the region, the TRAN ID, and the task number. So right away, we kind of know what the task number is and the TRAN ID that was running at the time of the storage violation, but we're going to get back to that a little bit later on. What we're going to do instead is show you storage manager summary, right? You can see from the summary that the domain was fine. I had storage recovery turned off. We'll talk about what that means a little later on, but I had all the protections set to yes, right? And I'm going to show you what the individual protections are in just a little bit. We can see the current DSA limit, and we can see how much is allocated and that we're not at SOS. We can see the same thing above the line. And we can see only 58 meg out of the 1,000 meg or 1 gig I have allocated is have defined as allocated, right? Now you can see the Grande DSA, that's a really big number in meg, and you can see I only have 1 meg really allocated. Then it'll give you some of the information like Mem Limit set to no limit, and where did it get its source from region 0. Now I'm using TRAN ISO, so it'll give you some information on transaction isolation, but then it'll take us to the DSA summaries. Now, one of the things I'll point out within the DSA summaries, if you have a short on storage condition or you have a storage violation, you'll notice that there are some flags for each DSA to tell you whether or not you're currently at SOS and how many times you went SOS, and it'll also show you storage violations. So right away, as we look through this, we'll look out for the DSA that has the storage violation, because I'm looking at a storage violation dump. So there could be more than one. I will point out that after the DSA summary, it'll show you what extents are allocated. So I have 1 extent allocated to the user DSA. Now, as you go through the different DSAs, you'll see this also only had 1 extent. And yes, I'm bypassing it because I'm looking very quickly to see 0, no, 0, 0, 0, right? So I know there's no storage violations here, right? So now we're on the read-only DSA, and you can see that the extent size is all 256K. I will point out back over here that the extent size in the user DSA below the line was 1 meg. And the reason for that is because I have TRAN ISO turned on. Otherwise, you can see the minimum is all 256K, and we had no problem below the line. As we go above the line, you'll start to see some more activity, right? Because most of my stuff runs above the line. The ECDSA had 16 meg of virtual storage allocated to it. And you can see it's also not SOS or storage violated. And here are all the extents, right? And you could see the size and how much is left over, how much is free. So there's a little bit of storage left in some of the DSA extents. Now, if there is plenty left in the EDSA lim pool and somebody asks for a piece of storage that was bigger than could be filled by the leftover pieces, then CICS would simply allocate another DSA extent to this DSA. So finally, that takes us to the user DSA. And in the user DSA, you'll notice the storage violation has a 1 in it. So right away, you know that the violation, or at least one of the violations, is in the user DSA. And you could see the 2 extents here. And so the violation has to be in one of these extents. And in fact, you can see that this one is completely free. So that tells us the violation is actually somewhere within that storage extent. Now, that still gives you a whole meg to go through, but nonetheless, you know where the problem is. So I'm going to pass the other DSAs because they're all pretty much the same. This one has a lot of stuff I should point out, right? The ER DSA is where we load read-only programs, so you'll see a lot of storage there as well. Okay. So let's get down to the subpools. Here's the Grande DSA. We're not using a lot of storage within the Grande DSA, but nonetheless, we have one extent allocated above the bar. Okay. And you'll see these other extents. The Grande user DSA has 0 meg allocated, and the shared DSA is 0 meg. Then it gives you an extent summary. He just basically shows you all the extents. And then what he does is he gives you the transaction manager transaction control blocks. Now, we're not going to look at these control blocks. I will show you that he didn't have enough room on a 132 column page. So he starts by giving you the SMX, the TRAN, and the TRAN token. Then he gives you some data over here. And then he has another list of these. They're the same ones. The only difference is he ran out of room over here to give you the rest of this stuff. So he does it in 2 blocks. And then it takes us to the task subpool summaries. This is where I wanted to get to. So you'll notice that tasks get storage out of 6 subpools. So we can see the TRAN number, and then we can see the subpool names, and I'm going to talk about them. But they all start with a letter, and the letter means something, and they end in the task number. And you can see the number of gets. I'm going to hit PF11, the number of frees, how much you have allocated, and over on the right-hand side, you can actually see the TRAN ID. Now, every task gets storage out of 6 subpools, right? So when you page to the bottom, it should bother you that task 202 right down here only has storage out of 2 subpools. How's that possible? Ezriel said you'd get storage out of 6, right? So how is it you only have 2? Well, first of all, I guarantee if we shift over to the right, the task is pay 1, because we saw that in the dump summary. And we know it's task 202 because there's the task number. So we know the storage violation is in one of these 2 areas, which is very important because we're going to see that these values are what we call the storage check zones. But we're going to get back to that. Before we do, let me just show you one other thing. And that is if you page down, you can see the domain subpool summary. So the domain subpools have individual names like AP_TCA24. So this is the 24-bit TCA, or let's find another one, kernel stack 24 extended, right? And you can always shift over to the right-hand side to see the element storage and the page storage that's being allocated. If I were having a short on storage condition, I'd obviously go through all the domain subpools and take a look and see which one of them, if it's one of these guys, is eating up all my storage. And I can do the same thing with the task subpools by shifting over to the right-hand side and seeing how much is allocated as well. But since we're not doing a short on storage condition right now, we're not going to worry about that. So any questions so far? No? Okay.
No, there's none in the chat, Ezriel, so you're
Good.
doing well explaining.
Okay, excellent. So now let's talk about these DSAs, right? Dynamic storage areas is where storage is allocated from. And as I mentioned earlier, you don't get a storage violation if you overlay storage in certain areas, right? So it's really over the task storage that you can get a storage violation. But nonetheless, somebody can actually step on a piece of storage. So how do you avoid being stepped on? Well, the answer to that is you protect the storage, which we're going to see in just a second. But before we do that, you can see there are actually 9 DSAs. There is this extended trusted DSA for security information. So even though I put it on the page, we're going to ignore it for now because we don't work with it at all. And over here, what you're looking at is the 4 DSAs above the line and the 4 DSAs below the line. And then you'll see I've highlighted in green these DSAs, right? The reason is the task data key identifies where you're going to get your task lifetime storage from. If it's user, which is the default, then your task lifetime storage will come out of the extended user DSA or the user DSA. But that depends on task data location. Obviously, if it's set to below, you're going to get your task storage out of the user DSA. If it's set to any, so default and default, you're going to get your task storage out of the extended user DSA. If you change this to CICS, it's going to come out of one of these 2. And if you do below, obviously here, and any, it's obviously going to be there. Now you'll notice I drew this picture a little bit funny. I drew a line here and a line here. Well, the line here is just to show you this is the 16 megabyte line. The line over here is used to identify the fact that the user DSA and the extended user DSA don't run any programs. There's no programs in these DSAs, only task lifetime storage. In fact, if you look in CICS, the loader doesn't even know that those DSAs exist because he can't load any programs into these DSAs. The reverse side of the equation is these DSAs have the ability to load and run programs. And so that's why I draw them separately. So we already saw a little bit about task subpools, right? CICS will allocate 6 task subpools for every task in the system. Each subpool is either for the user or the CICS DSA. So now you know why you get 6, right? It's because you get 3 for user, 3 for CICS, right? Obviously, what's the reason for 3? Well, you got below the line, you got above the line, you got above the bar. So when you add it all together, you get a CICS and user below the line, and above the bar, which gives you a total of 6. Now, these subpools are exclusive to your task, and the names have a certain meaning, right? We're going to see that in just a second, but obviously there's always a letter followed by the task number. So what does that actually mean? Well, the letter is the identifier of the storage. So M is CICS macro, so it's below the line in CICS storage. And then C is CICS above the line storage. So M and C are for CICS storage. B is user below the line, right? If you're using any user storage below the line, U is for user above the line. And then finally, we added the new ones for above the bar. We have G for the grande CICS above the bar, and H, I have no idea how they came up with the letter H. It probably only because it comes after G, okay? And that's user above the bar, right? And as I said, in my region, I only have 1 gig identified in my grande storage area in the CICS DSA. So even though I have H specified for each task, if you actually look at them, they're all 0, right? So when you actually take a look at one of the H and you'd go all the way over to the right, these are all 0 because I haven't done any assembler get mains, which is the only way today to get storage above the bar. Okay, so what is a storage check zone? A storage check, because we do mention it over here, over on the right-hand side, subpool name is reused for the storage check pool name. When you allocate storage in a CICS region, when you do a get main, you always get an extra 8 bytes on the front end and the back end, known as the storage check zone in most cases, right? And it's used for storage violation detection. Effectively, if I ask for 100 bytes of storage, I'm going to get 116. And CICS is going to allocate 8 bytes on the front end and 8 bytes on the back end, right? We're going to see what we do with that, but think of it as license plates on a car, right? We're going to see that if you overlay any of these so that the front and the back end do not match because you've stepped on one of them or both of them, then that's what we consider a storage violation, right? Now, he also does check the SCZ that it should have the correct value. So if you manage to overlay the front and the back end with blanks, he'll still detect it as a storage violation, right? Now, again, what does he do with a storage violation? Well, he'll produce a dump by default, right? There's also a sit parameter. You'll notice mine was set to no, but you could set storage recovery yes, and then CICS will try and fix the areas and return that storage for use. You could specify no. If you specify no, the task becomes what we call a forever task, and it sits out there holding on to that piece of storage until CICS recycle so that nobody touches that particular piece of storage. And there's lots of arguments whether to use storage recovery, yes or no. I'm not going to make any recommendations. It's really up to you. I tend to run with no because, you know, losing a meg or 2 of storage doesn't bother me. If I tend to start to lose a lot, then it's probably good that I have to recycle the region to free up the storage areas. And at least I could get a good dump that shows me what's going on there. Anyway, there are other types of storage areas in the old macro world, and they used to be called storage accounting areas rather than storage check zones on the front and back end. So the 8 bytes on the front and back end would start with a hex 85. It would give you some sort of length and then a chain pointer to the next piece of storage. Now, these were a lot uglier when they were overlaid, because if you managed to overlay 2 in a row and you go more than 2 bytes into the next one, you actually lose a piece of storage because the pointers to the next piece were actually in the storage area, right? This is from the old days. Well, obviously it didn't work out too well because you tended to lose regions more often. And so it was decided to kind of avoid these. So where do they still exist? They still exist in the world of terminal control, right? Why? Because nobody's ever going to modify terminal control. We're using less and less of terminals day in, day out. And so even though we're not going to show you a storage violation solution or looking up a storage violation in a storage accounting area, the principle of what we do is pretty much the same. And so you'll use the same concept to solve these problems as well, but we're not going to cover it. So let's talk about the types of storage violations. If you just do the math, you can figure out, it's really easy to figure out what you can get. The first one, and the most popular storage violation, is what we call a simple overlay. This is you shooting yourself in the foot. This is you, your program running, and overlaying the end of a particular piece of storage that you've allocated. It's the most popular type of storage violation. It's also the easiest to solve. Why? Because you kind of violated yourself. It's got to be one of your programs, right? We should be able to detect those. That's probably 80 to 85% of the storage violations I run into. Then there's the complex ones. They're a little bit uglier. That's where one task overlays the storage of another task. It's less likely to happen with some of the protections we have in place today, but nonetheless, it's still possible, right? Even with all the storage protections in place, because you could still get shared storage, right? And in the world of shared storage, there are no protections really. So you could still get them. They happen less often, and we'll give you some idea of how to debug those as well. Then comes the really ugly ones, undetectable. If you actually wipe out a piece of storage, but you don't hit a storage check zone, CICS will not detect it as a storage violation. The task will suddenly get these strange abends. You could have applications that were running for 40 years with no problems. Next thing you know, it's bending all over the place. And you take a look at it and something is just wrong, right? And that's usually because somebody has stepped on a piece of storage and they didn't happen to hit a storage check zone. The good news is if it's random, chances are one day you will eventually get a storage violation because it will hit a storage check zone. But if it's very particular to overlaying an application, they're much harder to detect, right? And generally, it's if you overlay yourself still, right? So those are still more popular. The most ugly one is the undetectable complex ones. The ones where I had an example where somebody was writing 1 byte, binary zeros randomly inside of a CICS region every so often. And that one took me 6 months to solve, right? So don't assume these are easy by any means. That was you overlaying CICS domain storage or unallocated storage. And in the case of the 6-month one, it was unallocated storage most of the time. So nobody ever detected it. And then every so often it would hit somebody who cared. Right? And because I had very little data, it was hard to kind of figure it out. But eventually we did. So what about causes of storage violations? Well, the causes of storage violations are user programs with incorrect lengths. This is the #1 reason, right? You do a get main, but you think in a different program that you did a different size get main. So you think you have more storage than you actually do. And you write past the end of a storage area and you hit a storage check zone. You have TWA or CWA, TCTUA, COM area length mismatches, right? You think the COM area size is 1 and the COM area size is a completely different size. Right? You link to a program passing it a COM area, you change the COM area size and you forget to recompile all the programs involved. It can cause all kinds of problems, right? Or linkage section areas. The other popular one is incorrect index or subscript values. You can get a runaway index or subscript or no editing of index subscripts, and that can cause you the same sort of problem where you just run away. And then here's the more ugly ones, right? Accessing storage without proper addressability. This is where you can run into modifying other transaction storage, right? Not clearing a free main pointer, writing to areas already free mained. You get an invalid address as a result of a set failure, uninitialized pointers, right? These can cause all kinds of problems, right? And then the last one I kind of pointed out here is hand posting of ECBs for canceled or terminated tasks, right? You get an area, you're supposed to post the ECB, move 40s to it, or post it, and it turns out the task is already gone, and you're just posting or setting values in middle of free storage, in middle of nowhere. So these are the types of things that can cause storage violations. So before we get on to the actual solving of the storage violations, let's first talk about protecting storage in CICS, because I tend to hear lots of different opinions about what they should do and what they shouldn't do and what the costs are, right? But at the end of the day, today machines are pretty fast, and IBM has different charging mechanisms for the use of CPU. And so, you know, I consider everything. So let's start with the first one. Let's just say, what are the MVS storage keys for all the DSAs when you start out with everything turned off, right? Well, let's start out even simpler. What's an MVS storage key? Well, there are 16 storage keys within MVS, and the lower the key, the more protection you have. So somebody who's running in key 9 cannot write to key 8 storage. And the ultimate key is key 0. The only person who can write to key 0 is pretty much MVS or the CICS loader, right? So if all the DSAs start out as key 8, then if you run with no storage protection turned on whatsoever, then everybody can overlay everybody else, and it's just pandemonium. It's like Pandora's box. You never want to run that way. So one of the first pieces of protection you can put on, and it is the default, so if you don't touch it, it'll be on, is rent pugum. Rent pugum protect will change the read-only DSA above and below the line to key 0. And by doing that, the only one who can touch key 0 storage is the MVS loader, which is what CICS invokes to load programs. Now, how do you get into the read-only DSA? So once you put the protection on, you got to make sure your programs, or most of your programs, are loaded in the read-only DSA. How do you do that? So the answer is you use the rent pugum equal protect, and you also make your programs or mark them reentrant. Then by default, they'll be loaded in the read-only or the extended read-only DSA above or below the line, depending on data location. So that gives you a piece of protection. The second piece of protection is storage protection, and the default is also yes today, okay? Storage protection will change the shared DSAs above and below the line and the user DSAs above and below the line to key 9. So what it's basically doing is separating out the system from the user, right? So the system is still key 8, right? System program will still run in key 8, and effectively it could still write to the shared or the user DSA. The difference is if you make storage protection yes, and your execution key of your application program is user, you will not be able to write to the CICS or the extended CICS DSA. Now, you could always link to a program that's defined with exec key CICS if you needed that ability, but nonetheless, it'll provide you with some protection. Okay. Now, finally, there's a little bit about transaction isolation. Transaction isolation is only going to work in the leftmost DSA, the user or extended user DSA. And what it has the ability to do is protect one user from another, right? And the way it works is there is all of base space. Base space is basically a transaction that's a system transaction, and he can write wherever he wants to. So you don't want to have too many of those. But for individual users that are defined with exec key user, we could have isolate yes or isolate no. Isolate yes with exec key user is the ultimate. That means that every transaction runs in its own unique subspace. Now, what's the advantage of a unique subspace? Think of it as a jail cell, right? The person that's running in a unique subspace, right, cannot affect other people in the system, but it doesn't provide him any protection at all. It's really interesting. Some people think that if you run a task in its own unique subspace, right, he gets some protection. At the end of the day, he doesn't get any protection. Think of it, if there's one guy in the jail cell and everybody else is on the outside, I could take a rock, throw it inside the jail cell and hit him in the head and kill him, right? But if he's in the jail cell and he has no resources available to him, he can't hurt me at all. So actually, Tran ISO is about protecting the entire system from the user. Now, obviously, if everybody's in the same jail cell, everybody's in their own jail cell, the entire system has some protection. But there are situations where two tasks need to communicate through storage. And in those situations, we would make isolate no, which still gives them tran ISO, but puts them in the common subspace. There's only one common subspace, so think of it as a shared jail cell. Inside that shared jail cell, the people can kill each other, makes no difference, but the world is still protected from them. Now, tran ISO is one of the areas that people don't know what to do. Should I turn it on? Shouldn't I turn it on? Should it be on in production or development or neither or both? The answer, I think, is you should certainly turn it on in development, right? Because you're hoping to catch storage violations before they make it out into the real world, which would be production. Whether you should run it in production or not is really up to you, right? There is a cost associated with it, both storage and CPU wise, as we're going to see storage wise in just a moment, okay? The last one I'll mention is command protection. It prevents using CICS as what we call the hired gun, right? If you do a read into and you pass in somebody else's storage area, then by default, CICS would have violated that area because he is the ultimate. He can write wherever he wants to. With command protection, yes, CICS will check the first byte of the into area to make sure it's yours. Otherwise, you'll get an AEYD append. It'll also check the address provided for set commands as well. Now, the default, of course, is yes. Right? Now, all those protections will only help you get less storage violations, but they won't solve the problem. So let's start with the storage manager internals. We're almost up to solving storage violations. The one thing I want to point out on this page is you'll notice the DSA sizes mentioned again, right? So remember I said the extent sizes are a minimum of 256K except for the user DSA with tran ISO, yes. Everything above the line is a minimum of 1 meg and above the bar a minimum of 1 gig. With tran ISO no, you'll notice that the extent sizes are all 256K below the line and 1 meg above the line and 1 gig above the bar. The big difference here is in the user DSA, do you see each user, right, will get 1 meg of, where is it? I'm sorry, I'm in the wrong place. Each user in the user DSA will get a page size of 1 meg over here and a page size of 64K over there, right? So how much storage is given to you is based on whether you have tran ISO turned on or not. So if you have tran ISO turned on, each user gets at least a meg of virtual storage. So if you have a max task set to 200, you have to isolate at least 200 meg to use for transactions running in your system, right? Whereas the storage size or the page size for individual tasks that you're running when tran ISO is no is a lot less. So the storage requirement is certainly higher for transaction isolated transactions. Okay. Now, we mentioned the 6 storage check zones. I'm just pointing out the fact that the storage manager transaction has the address of each of them, but we don't really need that. I'm going to show you an easier way to find them inside an IPCS dump. And then finally, this is what we want to get to. The subpool control area is the anchor for each of the 6 subpools. And once you know which subpool you're interested in looking at, you're going to see chained off the subpools are these things called SCEs for allocated storage. You can see the address and length of the storage at hex 10 and hex 14. Free descriptors look just like SCEs, right? They're the same sort of storage control block, but the difference is they point to free storage and they give you the length of the free storage. So if you have 1 meg of virtual storage and you only need, I don't know, 500K to start out, you're going to have an SCE with 500K, and the rest of your 1 meg is going to be sitting inside of an SCF. In fact, this is a better way to show it to you. So you're running in a transaction isolation environment, and what you're looking at here is, here's your 1 meg of storage. As you do get mains, for whatever reason, under the covers, or you do them yourself, storage is allocated and you get these SCEs. SCEs are managed as a push down stack. So this is the oldest one, followed by the newer one, followed by the newer one. In fact, this is probably even older because you'll see there's even a free area in between. Now, what happens is CICS will only keep one SCF if the storage you've allocated is all contiguous. The only time he needs more than one SCF is if you suddenly allocate and free a chunk in middle of an area. So he'll have to keep two SCFs to manage that storage. Otherwise, in general, you only see one of these. So SCZs are in push down stack or most recent to oldest order, and SCFs are in virtual ascending storage order, right? We're going to see why that's important in just a second. So these are just some notes for you to remind you. The address of an SCE points to the SCZ, which matches the subpool name, i.e., when you're looking at it, the storage area we're provided by the control blocks include the storage check zones, right? So that's what this is saying. The get mained area that's given to you is the address of the SCZ plus 8. So you're always given 8 bytes later. It's important to remember that when you're doing searches for storage, right? Now, the size of a get main is at least 16 bytes longer, right? Because you have to have an 8 byte on the front and back end storage check zone. In fact, today the minimum get main is 32 bytes. So even if you ask for 1 byte, you'll get a minimum of 32, which is 8 byte storage check zone on the front and back end, which is 16, and then 16 bytes is the minimum get main, right? There are no chain pointers in SCZs, nothing to break like the old SAAs. CICS checks the virtual storage on free main of the task. So here's the next important thing. When do we detect storage violations? By default, it's when the task ends. It can happen earlier if we turn on some additional checking, right? Now, if the front and back SCZ don't match, we get a storage violation, right? And then the last important thing, besides for task end detecting storage violations, is a task that actually is experiencing a storage violation may actually complete successfully or unsuccessfully. Has nothing to do with the task. You see, if the task ends successfully, it's during storage cleanup that we detect the storage violation. So the task could have worked, right? However, chances are if there's a violation and you're violating a particular area and you're putting bad data in there, then maybe the task is abending with an ASRA, right? And because of that, the task is in the middle of abend processing, and during cleanup, we happen to find a storage violation. Now, if you actually get a transaction abend, I usually start there to try and solve the storage violation. Why? Because a transaction dump is a lot smaller than a system dump, and it is a lot easier to go through. So if you find out that the task abended, your first step is to go through that and take a look and see if you can solve it from there. So if not, where do we start? So now we're finally getting to how do you solve a storage violation? So the first thing I always tell everyone is exception trace, whether you like it or not, can't be turned off. Everybody has exception trace turned on, right? Regardless of whether you turn off everything else there is in trace. So if you're in the dump, use option 6 and issue this command, verb exit dfhpd, where the version release modification for 5.6 is 730. Do a tr equal 3, which will give you summary, abbreviated trace and full trace, and do TRS, trace selection criteria, equal exception with a less than and greater than sign around it. Do a find of the exception. 15 is the column I found it in, but you could just do find exception last, and you should find a storage violation message. Now, SMOFOC is just the most popular one, but you could find a different message. You can always look it up using good old Google, and then you're going to look at the parameters in them. So I'm going to do the same thing live, and I'm going to jump over here for a minute. And instead of doing it here, I actually used IPCS in batch to print off the traces. And that's because my trace tables are really large, and paging through it, sometimes there's delays. And so I wanted to make sure it was quick for this presentation. But if I take a look at this one, if I page down for a second, you'll see that this is the TR equal 3, TRS equal exception. And I said, find star EXE star 15 last, and it'll take us to the exception. Now, we mentioned that this will give us the failed address right there. Now remember, this address is of the storage check zone. Now you'll see the address again in item number 2. You'll see the length over here. And then what you're going to get is the beginning and back end storage areas, right? So if you remember from the presentation over here, you can see option number 4 is the first 512 bytes. 5 is the last 512 bytes. So first and last. So if we page over to the right, the first piece right away doesn't look like a storage check zone to me. So I know the top of this storage area is violated. If I page down, and I make sure to go back to prove that I'm not crazy here, the ending area is not violated. So actually I have a front end storage check zone violated, the back end is not violated. But what's really important is to remember this U0000 task 202, yeah? Because that's how we're gonna find the violated area. Good. Now I could have looked at the data preceding or after, but I'd rather look at the storage areas themselves. Now, I've already mentioned to you that in the dump summary, you can see the tran ID was pay1, the task is 202, right? This is the Apple ID. But what I'm showing you here is that the message code 0F0C, add an SM on the front of it, is the actual violation type. So that's why I looked up message SMOFOC, and that's why you saw that this is what I Googled, and I found that message. So how do we try and solve this, right? Well, because I know the task itself, I'm going to issue this command, verb exit, right? TR equal 1 is just the summary, TRS task ID 202. I want to find the task itself. Why do I want to find the task itself? Well, the one thing I can tell you about storage violations is if you can find the task itself, so here's my trace, and you can see that I did the TR equal 1 TRS 202. And because I know the address of the area from before, which is 2270412, right? He said 04120 because he pointed us to the front of it. But if I do find 2270412 and I leave the 8 or 0 off the back end, I can find the get main. So here is the get main. Why do I care about the get main? Well, the first thing I'm going to do is shift over to the right, and this is going to show me the identifier of this trace entry, and I can look at that in full trace. I can use it to find where the get main was in a later trace. So I'm going to remember that number in just a second. But why is it I'm looking for task 202? Well, task 202, there's the allocated storage, and as I page through this, eventually at the end of this, I'm going to see the exception trace. 202 did a lot of work. I'm going to see the exception trace, and I somehow missed it. Fine. Oop. I went too far now. No, actually, he doesn't show it to you when you just list the task, but that's okay. Let me show you the next example. So now you know where the get main is, okay? Now that you know what the get main is, right, you find, and I'll blow this up again, you find the area and you find this number over here, and then you use a plain old TR equal 1 and you find the start of the get main, which is this number over here. So let's do that right now. So I'll go to my third trace here. This is just a plain old TR equal 1. You see that? And what I'm going to find in there is 923083. And what I'm going to do is I'm going to manually page from the get main all the way down to the exception, which I will see in this one, and see if any other tasks ran. So you'll see only 202 is showing up, and then I see task number 3, okay? Now, task number 3 is running on the socket listener. So I know it's CSOL, but you can always go to the AP domain and make sure task 003 couldn't have done the violation. He couldn't have, it's CSOL. I see task 56, we'll check out who he is in just a second. But as we page through this, are there any other tasks till we hit the exception? And I will tell you, I've done this already. And until you hit the exception, which is about to show up, this is during task cleanup. Don't tell me I won't see the exception, Ezriel. That's what happened. There it is. So until you see the exception, it was only task 3 and task 56. Now, if I wanted to see what that task was, I can go verb_x. If I can spell today. And I could look to see who task 56 is. Task 56 is CSIR, right? Which is just used for TCP/IP communication. So he couldn't have caused the storage violation. By seeing what I just saw, I know that this is a situation where I had to violate myself. Does that make sense? Because if no other task ran in between the time I ran, right? And I did the get main, and then I had the violation, then only I could have violated myself. Now, without going through every piece of trace here, you could look at all the links and loads, and you'd find out every program that could have caused that violation, okay? So it has to be one of those programs, right? And you could trace through and try and figure out which one has an incorrect length or a subscript that's running away. I will point out,
Ezriel, can I just interrupt you? There's a question from Steve Wolf. He says, my DFH SM0102 does not include trans/task. Is that a new CICS feature?
Say that again.
My DFH SM0102 does not include trans/task. Is that a new CICS feature?
No. It should be there. He's talking about in the dump summary message, it should have tran and it should have task. Yeah, that should appear. But yeah, I guess there are some situations where it will not appear, right? And I guess it would depend on the CICS release. I'd have to go back and take a look, but tell Steve I'll look that up for him, right?
Well,
but
Joanne Levin's just suggesting it was new with CICS 5.5, and you're
thank you.
working on 5.6 now, are you?
Yes, I'm working on 5.6. So yeah, but don't worry about that, right? Because you can always figure out the transaction and the task, right? When you get to the exception condition, once you see what the area is that's violated, which is what we're going to pretty much do next, right? You'll be able to figure out the task just by the storage checkzone, right? It ends in 202, so you know the task itself, right? And you can always go back to the transaction manager. The transaction manager will show you the tran ID for task 202. So you can always get that information prior to version 5.5 and 5.6 is by looking at transaction manager equal 1 once you know the task number. And you will know the task number because you saw the U000202, right? So you know task 202, and then you look up XM equal 1 and it'll always show you the tran ID, yeah? So that will work. Now, since we're on this page, AP equal 1 in our case will show you nothing. PG equal 1 will show you nothing because that piece of storage has already been cleaned out. So unfortunately, you won't be able to see that there, right? But the transaction manager will show you the tran ID and the task number. So let's solve this. This becomes the easiest thing to do, right? So let me just show you how I actually find the violated storage areas. So I'm going to go back to my dump, right? And I'm going to do an SM equal 3. Now, the reason for 3 is I need the detailed information to get to the control blocks. Now, I already know my violation is in the subpool control area U00002002. Cool. Yeah. So you do a find for SCA dot whatever your storage checkzone number is and hit enter. Now, we also know it's the user. So underneath the subpool control area, you'll see all the allocated areas are SCEs. How many of them do I have? I have 3. And then the free descriptor is down here. And if you look at this, it's a push down stack. So this is 227.0.0.0.0 for a length of 3.0. And the next area, amazingly enough, starts at 3.0 for 420. And if you add them together, that's the next piece of storage. So this is all contiguous, okay? Now, we know that this is the area that's violated. But I'll show you, you can run IPCS without losing this page by issuing IPCS list, and then you just copy this address. And then for a length of hex quote, and it's 8 Charlie 40, it's easier for me to type that, and you hit enter. Now you'll notice I have the violation over here. It says JIC. But if I max to the bottom, sure enough, the storage check zone is still healthy there. So if you hit PF3, that says the violation was at least on the page before, I hope. So what I do is I do ret P. I pull up the command I had before, and now I'm going to change the address to 3.0.0. I'm going to look at the prior area, and its length was 420. And you can see the top end storage check zone is perfectly healthy. And if I max to the bottom, you can see it says circle is meh, and then JIC from the next page. So I know the violation occurred somewhere between here and the top of the next page. Now, this is a silly example. Obviously, if you can recognize the storage area, it'll help you identify who did the violation or which one of the programs you found. Now, of course, to know programs, you need trace. And sometimes you might have to turn it on to solve extremely difficult storage violations. Otherwise, the only thing you have to work from is the data. And it's really easy to find. Find the SCA and then look at the SCEs and SCFs. Now, this one should be perfectly fine. Just to show you that, if you wanted to look at all the areas, you simply put it in there. So this is 227.0.0.0.0, and its length is 3.0.0. And I guarantee you, well, I don't know. Let's see. Storage check zone at the top is healthy. And I just do M and PF8, and the storage check zone at the bottom is healthy. So you really can only try and identify the violated area, right, to help you solve the problem. And the instructions are right here on this page. That's exactly what I did. Yeah. And so hopefully that'll help you find the violation. If that doesn't help, you can also use the storage violation detection routine, CSFE. The use of CSFE just allows you to capture storage violations earlier, right? You can use check task storage current, or for terminals, you can use check strum current, right? Obviously, task is the one that I tend to use. Now, if you run this, just beware, you're going to use a lot more CPU, because now every time there's a get main or a free main, CICS will check all the storage areas associated with the task. The hope is you catch the violation a lot quicker to the when it was violated. Notice if you're only catching storage violations at an end of task, it's kind of hard because the task could run for half an hour. Well, could run for, I don't know, 2 seconds, right? So the violation could have happened a long time ago. So IBM gave us this storage violation checking facility, and when used, it can help solve the problem, or at least find the violation earlier to when it happened. You get an SMO 103 dump instead of SMO 102. But just, again, keep in mind, it'll cost you a little bit more to run it. And again, trace is still cheaper than this, right? So hopefully that just shows you a little bit about checking storage, right? How to find the violated area, hopefully how to find, using trace, the programs that were in control, whether or not any other program could have stepped on you, and then ultimately how to protect whatever storage areas you can protect. So with that, I will open it up to questions.
Great, thanks. If people can put questions in the chat, please. All right, here we are. Collins Pierce is asking, is there a way to tell if the violation was found during the transaction's execution or at the end of the transaction?
Yeah, the only way to find a storage violation while the transaction is executing is with the storage checker, CSFE debug, right? Then you could find the storage violation while the transaction's running, assuming it does any get mains after the violation occurred and before the task end, which is most likely because get mains and free mains are occurring all over the place. So if you use the CSFE debug, right, with the check storage equal current, it will find the violation a lot sooner while the task is running in most cases. Yeah. But again, it's quite expensive to run that. Just keep in mind, realize every get main, every free main, we're going to go through the entire storage chain for the task, right? So before I would use that, I would prefer to at least turn on some trace for the transaction and see if I at least can, because if you get the storage violations, they don't tend to go away by themselves. So if you don't tend to run with trace turned on, my suggestion is when you get storage violations, look at the area. If that doesn't help you solve it, at least turn on trace for a short period of time, hopefully getting a storage violation with trace to at least identify whether any other programs ran while you were running and whether they could have violated you, whether the storage belongs to them, or what programs were in control from the time of the get main till the task ended and you saw the storage violation, because it had to be one of those programs. There's no other choice, right?
Okay, brilliant. Let's see if anyone else. I can't see any more questions. Okay, I mean, the thing is, if anyone does have any questions, you can email me. My address will be on screen in a minute, and I'll pass them on to Ezriel, and I'm sure he'll get back to you fairly promptly with an answer.
Yeah.
So, can I thank you very much, Ezriel, for being with us today? And as usual, can you assume that you're getting a virtual round of applause from your virtual user group?
Thanks.
That's brilliant. Let's just finish off. I've only got a couple of slides, so it won't take me very long. Okay. Right, no news. Articles, I've only found one article, and that's on to develop a JMS application for CICS Liberty by Phil Wakelin, and it's on the tutorials section of the IBM developer website. Feedback request is there to remind me to ask you for feedback about this virtual meeting. And like I said, there's my email address there, so you can use that to email me any further questions. So coming soon then, well, look at that, 2020 so already. 11th of January, we've got Wendell Lovell from McKinney Systems. He's going to be talking about CICS application development, diagnosis and tuning. And following on from that, we've got IBM's Joe Winchester speaking on the 8th of March. And he's going to be talking about CICS, open source, and Zoe, depending on how you pronounce it. So a couple of good things to start the year with. Oh, I wanted to mention the Arcati Mainframe Yearbook. I know in previous years, a couple of people have done the survey. So if you do want to complete the survey, tell people what it's like at your site, you do get a free copy of the survey when it's been written up and completed. That's before publication. So that's at teched.com/Amy22 in capitals, user survey 22. And if you're a vendor and you want to get a free entry in the yearbook, then again, that's Amy22 vendor entry. Please, if you can do that, that would be great. And of course, we're on social media. If you're posting on anything, our hashtag is #virtualcics. Our links are all on the homepage of our website, so there's no need to try and remember it from this slide. Okay, well, that's all for this meeting of the Virtual CICS user group. Can I thank you all for attending? Thanks to Hostbridge Technology and Rocket Software for sponsoring our user group. And of course, I'd particularly like to thank Ezriel Gross for his presentation. So that's it. Thank you all very much for joining the meeting. And I look forward to seeing you on the 11th of January next year. So thank you all and goodbye.
Thanks, Trevor.